Hello everybody, welcome back. Today we're going to be reviewing our transformer protection, connecting all the things that we've done so far in the course. So over the last couple of weeks we've learned a lot about transformers, how they're a key asset in our distribution system. And we learned about how overcurrent events, either from an overload or a downstream fault, can damage a transformer through a couple of different mechanisms. Either through excessive heating, which causes the oil to degrade in your connections to heat, which can make them become loose, or your insulating oil to degrade, or your insulation itself to degrade, and accelerate the aging, which leads to premature failure of your transformers. And then the bigger one, which is mechanical damage. So if you get a really high current impulse headed through your transformer, that comes alongside with a really high intensity magnetic set of forces. And those can damage things. They rip leads off of bushings. They cause transformers to crush the insulation that they're using and thus fail. They can displace transformer coils. All kinds of weird stuff can happen as the magnetic forces literally tear the transformer apart from the inside. Now, we also learned how the IEEE offers a standard for that, and it's been widely adopted by Canadian utilities. So that's what we're going to be using here in this course. And for transformers up to 500 kVA, which is the majority of our distribution transformers, certainly all of the ones serving our residential, low-density residential customers, the IEEE defined a withstand equation here, and this is the form that we've been using more in our class. And that withstand equation represents a boundary, the edge of which anything above that is assumed that the transformer is going to suffer some damage, and anything under that, it's assumed that the transformer is going to be A-OK. Now, just because you cross that line, you have to assume the transformer is not going to will be damaged if you cross that line. So that doesn't mean it dies immediately. That doesn't mean that it gives up violently and suddenly, but it means that you've damaged it. That's the assumption that you have to make. So the objective is to make sure that we don't allow our currents and times to cross that line. And then the other thing we looked at was our inrush behavior, and this is a couple of different things play into that. There's, that initial very short period of time when you're just powering things up, and our transformer cores, which have that magnetic tank we talked about, which provides a back EMF or a back pressure, which is why a transformer doesn't behave like a short circuit, even though if you look at them from a static perspective, they look awful similar. So while you're setting up that magnetic tank and filling it up and getting that back EMF established, you get some very high current flows. And then after that's all resolved, you still could be in a situation where you've lost all your load diversity. And now you have some serious overloads while that load diversity gets reestablished. Think about your long power outage in the hot summer day, and you turn the power back on, and everybody's air conditioner and everybody's fridge and everybody's freezer and everybody's everything all wants to run at once instead of taking their time and cycling through things. And so if you plot these two lines, your inrush curve forms a boundary between what is considered the regular operating region, and anything beyond that is considered a fault. And our transformer damage curve, shown in red, gives you anything beyond that, it assumes that the transformer is damaged, and anything below that, it's assumed the transformer is fine. And if you combine the two, this gives you a region where you have a fault, but the transformer has not yet received damage, and this is where we want to do our protection. This is where we want our fuses to be operating, is in this region. Let's do an example. So let's choose the correct fuse to protect the following transformer. 50 kVA fed 4.8 kV. First step, let's determine our full load amps. Please check your units, make sure they're on the same base, so kVA to kV, VA to V, or you're going to get unusual answers. And that's going to give us, in this case, 10.42 amps. So if we are flowing 50 kVA, we're going to get 10.42 amps if our transformer's fed at exactly its rated voltage of 4.8 kV. And from there we can determine our inrush values. Inrush values have been determined empirically, and so it is this table. And this table is part of the table is always going to be the same. But these multipliers are per unit, and you can't plot per unit on a graph. You have to plot time in seconds and amps, current in amps. So what we're going to do is we'll multiply through by our full load amps for each line, and we'll get some currents in amps and some times in seconds, and we're ready to plot. Next up, we're going to determine our damage threshold. We're going to pick some times in seconds. We're going to use our equation, and we're going to generate some multipliers. And those multipliers are per unit. These two are going to be the same for every different transformer. Keep in mind, this is unitless. You can't plot it on a TCC graph. So again, we're going to multiply through by our full load amps, and we're going to end up with a current in amps. Now we've got time in seconds and current in amps. We're ready to plot our damage threshold. So we're going to start out. Now we can plot these things to the graph. Again, we're going to do inrush in black, and we're going to do our damage threshold in red. So we start out 260 amps for our inrush curve. There. 125. 62. And you should see that these points start to form a straight line. If you're finding that your line is wavy, check your plotting. Something's gone amiss. And we can continue plotting all the way up, and when we're done with that, we're going to start on our damage curve, starting at 36, almost 3,700 amps. 2, 3. Plotting in red. $368. Plotting the rest of the way up, we end up with something that looks like this. So your damage curve should be perfectly straight. If you find that it's looking wavy, again, check your points. Your inrush curve should have the lower 4 points perfectly in line. And then the last point, you're going to find that this has a little bit of an elbow to it. But these lower 4 points should be aligned perfectly. So we take a look at our fuses that are in our protective margin in between these two graphs. Taking a look at the 12K fuse, we can see that the 12K fuse has a couple deficiencies. It tucks underneath this inrush line, which means that the 12K fuse has an opportunity where it would operate when no fault is present. Remember, if we're on this side of the inrush line, it's assumed no fault is present and everything is working as intended. So for our fuse to operate here, would be considered a nuisance trip and a protection failure. You don't want to be putting your customers in the dark for no good reason. The power would be out on our hot summer day, it comes back on, Everybody breathes a sigh of relief, and somewhere around 5 seconds later, it goes out again, and they wonder why. Have to call the utility, and as a utility worker, you're going to get there, and there's going to be no problem to find because we tripped on a lack of load diversity. It was a protection failure. That should have never happened. If we take a look at our next fuse up, or 15, we can see that we clear our inrush curve, which is good, but we're beginning to touch our damage curve. And so there's the chance in this case, be it ever so slight, that we might just touch that damage curve at the very top out at 100 seconds before our fuse finishes clearing. Now, if you find yourself in a situation where you have to make a decision, none of the options are grand, right? No, there is no perfect answer, and now a compromise has to be made. It is preferable that you take the larger of the two fuses and you accept your exposure here rather than risking a nuisance trip here. That is not the preferred option. This is the preferred answer. That's our preferred risk. We don't want to deal with the risk of an operation down here. So because of that, we're going to take the 15K rated fuse. Now we're going to plot our lines again on an NX curve. Around 63, so that's in the middle. When you're plotting on the NX graphs, there's not a lot of value in plotting on the last two divisions. There's nothing going on up there, so plotting your lower divisions is entirely sufficient. And then we can plot our damage line. And those are looking like they're pretty straight, so it's likely I did an okay job putting my plot in, doing my interpolations. So we connect the dots, and we can see now when we spoke about current limiting fuses, we always said you want the largest current limiting fuse that you can accept. So in this case, the 40 NX is an interesting pick because we can see that it fails right around 23 milliseconds, no, 33 milliseconds. It will stop protecting this transformer, right? So that's 10, 20, 30, so right around 33 milliseconds. It's going to stop, which is 2 cycles. It's going to allow this won't guaranteed to have cleared before the transformer is damaged. But our transformer, our expulsion fuse, only needs the current limiting fuse to cover for 1 cycle, or about 16 milliseconds. So in this case, the 40 NX fuse is going to be acceptable. So we're going to pick this guy. If the 40 was not sufficient for some reason, then the 25 would be a very clear and easy choice. So we combine these into one graph, and we can see, oops, okay, switched over to a T here. That should be the K speed. So we can see we've got so the correct answer, by the way, was 15K 40 NX. Carrying on with our example here, We can see we've got our expulsion fuse sweeping through the middle. I've put an extra highlight on the max clear. As we can see, all along here, the expulsion fuse clears, expulsion fuse clears, expulsion fuse clears, and then we get into these higher current events, and we can see both fuses will melt, but the expulsion fuse will clear. And then at this point here, you can see both fuses melt, but the current limiting fuse now clears. And what this does is it gives you this sweep where it's the expulsion fuse that acts to interrupt, and then you get to here, and then the current limiting fuse acts to interrupt. And what that does in practice is it cuts this tail off the end. Let's do another, giving us a full protection of a perfect protection of this transformer all the way along, with the possible exception of this very tip here on the 15K, which we already discussed. Let's do another example. This time let's do a 75 kVA. Again, fed at 4.8 kV. We'll go a little faster through the example this time. We start out with our full load amps. We build our inrush table, keeping in mind that this is going to be the same every time. We multiply in our full load amps calculated above. We get some currents. Now we have time in seconds, current in amps. We're ready to go in terms of plotting that. Now we're going to go and calculate our transformer damage threshold, our times, which are always the same. We can use our equation to figure out our multipliers, keeping in mind our multipliers are per unit, they're unitless. We're going to multiply in our full load amps rating, and now we're going to get out of that a current expressed in amps and a time expressed in seconds, and we're ready to put that on our graph as well. So now we've got everything we need to start plotting on our TCC families. Let's do another K-speed example. So again, black for our inrush and red for our damage. We can start plotting our points. So we plot about there. And things should be looking pretty straight. And we plot all the way up. In the interest of time, I'm only going to put a few points down. And 552. Shaping up to look like a pretty straight line. So let's finish plotting our points and connect the dots. We end up with here. Good stuff. Let's take a look at our options. So our two promising options that we're looking at are our 20 and 25K fuses. However, our 20K fuse has a violation down here where we're crossing into our inrush curve, and yet our 25 is going to expose us to a little bit of risk around transformer damage out near 100 seconds because we might not clear before we cross that line. However, in the event that we have to make a compromise, we want to choose the larger link rather than the customer inconvenience associated with a nuisance outage. So we're going to pick the 25K. Keeping in mind that there's a compromise being made here versus here. Now we can pick our companion fuse, or our current limiting fuse. So we're going to plot our points again, just as we did the first time. And we can see from here that the 40K fuse looks like a really good fit. So let's take our 40K NX fuse here, because that's going to give us the best coverage of the three, keeping in mind that we want to get the largest companion fuse possible. The 12 and the 25 would both give us good transformer protection. However, as we go to the smaller fuses, that means the current limiting fuse operates on more classes of more faults than it would have otherwise. And we always want if we have the option, we want the expulsion fuse to act, not the current limiting fuse. So we want to pick the large fuse so we get the least exposure for our current limiting fuse to act. Putting those on the same graph, we can see we have a we have our little bit of exposure here at the top. We have a little bit of margin between our inrush curve and our fuse minimum melt, which is ideal. And down here we can see we have a nice clean transition between the expulsion fuse and the current limiting fuse acting. So we have down here at this end, we have perfect transformer protection, and up here we have a compromise that's been made. So going forward, I'm going to be asking you guys to generate transformer protection graphs. And this is what they should look like. They should have these elements on them. They should have an inrush line, a transformer damage line. We should have a min melt and a max clear for our expulsion fuse. We should have a label on our expulsion fuse. We should have a label for our current limiting fuse. And then we should have a max clear and a min melt for our expulsion fuse, or our current limiting fuse. You don't have to have an emphasis on the maximum clear. The line weights between your min melt and max clear would be the same. I've only got them highlighted here to showcase the transition between the two. So these are the common elements that I'm going to be expecting to see on all of your graphs. And there are a couple different techniques that you can use to generate these. And there's a couple companion videos I'm posting on the lecture today where I go through examples of how you generate these. So there are 4 paths available. 3 of those are really accessible to you guys for the purposes of our class. The first choice is we use some professional distribution analysis tools. This is some heavyweight software used in industry. It's not easy to use. It's not easy to come by. It's very, very expensive. Has a very steep learning curve and is really not well suited to use in this class. So that's about as much as I'm going to say about that option. The most low-tech option is you can assemble a curve like this by printing out a blank and the appropriate current a blank cop TCC graph, and then the appropriate series families of fuses, and overlaying those, stacking those pieces of paper, and then putting them on either a light box or pushing them up against a window during daylight hours, and you can trace through that top page. You'll be able to see the graphs underneath right through the top page, and you can trace them onto the page. If you want to go slightly higher tech, you can do the same thing in digital form, and I'll be doing that in one of the companion videos, where you can use a graphics editing tool of your choice, layers and transparency, to allow you to assemble these curves. The last choice that's available to you is you can use S&C's coordinate. Although getting our lines to look exactly right does require the use of some manually generated files. I'll show you how to put those together, and once you're comfortable with it, that can be a very quick way of getting things done. Thank you very much for your time. I look forward to continuing to learn with you guys. Check out those companion videos and give the homework a shot. And as always, if you have any questions, please don't hesitate to